All right, so today we basically are going to take the same stuff we learned yesterday and like just kind of look at it from a different angle. Like already by now you should know that an exponential kind of looks like that. Do you know that already? Okay, good. Then would you please sketch that for me? I'd like you to circle the starting value. And I'd like you to tell me what its domain and range would be. Just by looking at this graph, you can say, oh, I know the domain is from here to here, and the range is from there to there. Remember, domains are this way. All right, so here's the starting value. And the domain, if you go this way to this way, is there anything stopping this function? Oh, it keeps going forever. Negative infinity to positive infinity. How about the range? Is there anything stopping it on the low end? Yeah, it'll never go past what? 0. So 0 to what? Anything stopping it on the high end? Nope. All right, domain range. Now how about asymptotes? Is there any asymptotes? Yes, there is, because if it'll never touch 0, there must be an asymptote down there. So it's y equals 0. Okay. Now how about end behavior? Well, basically that's the behavior on the ends. So way over here, how low would it go? Come on. What's the lowest it would go? 0. And way over here, what's the highest it would go? It would go to infinity. Okay, so it's basically the limit of the function, and you can either do the left end limit or the right end limit. Lim of the function as x approaches negative infinity, that's the left side, would be 0. And the same kind of thing on the right. All right, so that's pretty much just review. We just threw in a couple words you knew from the past, domain and range, and then reminded you that these have asymptotes. All right, if I had y equals e to the x, do you remember what that would look like? Same thing, right? Okay, how about if I said 1 over e to the x? Is that growth or decay now? It's decay, because you have a fraction. It's like 1/3, except it's 1 over 2.7. So it would look like that. Yes? Exactly, that was the one I was just going to do. I was going to change this instead of that, how about e to the negative 1? That's the exact same thing as 1 over e. Exact same thing. E to the negative 1 means 1 over e to the x. Okay, so this and this would be identical. Both of them are decay. All right. Remember, the graphs are not super, this is not a graphing test that you're walking up to here. It's going to be a test that's kind of more sketches. So you don't have to worry about many exact points. All right, how about this kind of a graph? 18 over 1 plus e to the negative x. Make a sketch for me of that. It's called the basic logistic function. Hopefully that 18 on the top gives you a big clue on what you should do. Okay, I hope you knew that it kind of looked like this. And then the asymptote goes right through there. And what's it at? 18. And the other asymptote that you don't think about much is right there, 0. How about the domain and range of this? What's the domain? What's a fast way to say negative infinity to positive infinity? All reals. Very good. So the domain is all reals. Okay, how about the range? 0 to 18. Very good. Okay. How about if I were going to give you this problem, y equals 7.5 to the x, and then I asked you, what's different about this? Y equals 7.5 to the 2x minus 3. First of all, is it different? Yes. Has it been moved or what? I'd like you to right now write down what are the 2 things you would have to do and in what order. The order matters. For the 2 things you'd have to do to get this one to turn into this one, you'd have to do this and then you'd have to do that. Make sure you do it in the right order. That's one of those things you get tested on so many times this year. You've already been tested on like 5 times, the order. It's probably going to come up again. All right, well, there's nothing happening on the outside. When you compare this one to this one, there's no difference on the outside here. This one compared to that one, it's the same thing. Okay, it's all happening on the inside. So if I go to the inside and I look in here, what would normally happen first? Times 2 or minus 3? What's normally first? Times 2. But since we're on the inside, that isn't first. And minus 3 is the first thing, and that's right 3. How many of you knew to start with that? Raise your hand if you did that right. Good. Because again, normal situations, multiply happens before subtract in the normal PEMDAS order of operations. But we're doing inside the work, and that means you do it backwards. So now, if the other thing has got to be last, that thing is a what? Stretch? Horizontal stretch, right? Horizontal shrink? Yes. What's the factor? Good. That always has to be a fraction. In this case, that has to be 1/2. Okay, good. Next. Oh, what if I threw in a negative somewhere? Like, let's say I threw in a negative right there. No, that negative does not make a stretch. That makes a horizontal reflection. Okay? Horizontal reflection, and that means a reflection across which axis? Reflection over the y. Now this and the reflection thing, it doesn't matter what order, so I can put the reflection last if I want to. Why do they not matter the order? Because these are both multiplies. So they can be interchanged. The order doesn't matter on those two. Reflection over the y-axis. All right. Let's talk about how we can make those problems that we did the other day like this. We'd say, how can you write an equation for this? And I give you this as like 0, 3. Don't even do this one, but do you remember doing this kind? If that's 3, it doesn't make sense. That's 3. That must be like 12, 9. That didn't take long. Good to have you back. All right. So if I give you 2 points, you're supposed to be able to, this is like R2 level stuff. It's supposed to be pretty easy. Maybe an easy R3. Yeah, maybe it's one of the easier R3s. Y equals AB to the X, and then where do I put in the 3? 3 goes in on the A. Because the starting value is 3, so 3 goes there. Then where do I put the 12 and the 9? Yep, those 2 spots. Okay, well, how is it different today? Today, we're going to give the time. 1992 is when I started teaching. And when I started teaching, let's say that there were 14,500 people. Nope, I'm wrong. 44,500 people in Minnetonka. Okay? And in the current year, 2014, let's say that there are 70,000 people. Do you get how I effectively just gave you 2 points? All right. Of the 2 points, which one's like the start value? 1992 or in 2014? 1992. But you guys know that the start value is supposed to actually be where the time is 0, right? So don't forget to do this part or it gets all messed up. That has to be turned into a 0. Can I do that? Yes. If I change the other one, how many years is it between 1992 and 2014? 22. Very good. So I can cross this off and make it a 22. That's an important step. Do you get what I just did there? I said that the starting value is supposed to have x be 0. So I changed my time from 1992 to 0. I have been teaching here a while. It's kind of scary. Any of you guys know Mr. Tuthill? He's one of the teachers here. He's been teaching here like 10 years now. I taught him. He was a student out in the classroom, and now he grew up and went to college, got a job here, and he's been teaching here 10 years. I actually taught him in 8th grade. So that was kind of weird. So I'm expecting when his kids come through, it might be the first one where I taught him and then I taught his kid. I'm expecting that to happen before I retire someday. He's got a kid who's in them like elementary school, so just a few more years it could happen. All right. So if I'm going to do this problem, I got to start with y equals a b to the x, except I know a. What's the a, the starting value? 44,500. Okay? And then, do I know b? No. What do I know? Y and x. They come from these two, and they go into the right spots. Do it. Use a calculator and solve it. I'll warn you, at the end, you're going to take something to the 1 over 22 power. It's weird. Your answer will be like, 28 to the 1 over 22 power. When you do that, you need to do a parenthesis around the power, otherwise it'll get screwed up. Grab a graphing calculator. If you want to borrow one of mine, that's fine. Leave me some collateral. I have another one if anybody else needs one. Okay. What? Yes, I do. Come on up. Okay, so here's what I wanted you to do. I wanted you to be thinking, okay, y is the time. No, x is the time. You should know that. X is the time. So that's 22. And then the other number must go here in the y. 70,000. This is a lot of work, but I'm going to figure out b when I'm all done. And then I'll be able to write the whole equation out. All right, so now I'm dividing by 44,500. Dividing by 44,500. B to the 22nd. And what is this number here? 70,000 divided by 44,500. 1.57 what? Thank you. And then I put that to the 22nd power. No, 1 over 22nd, sorry. 1 over 22nd power. And don't forget to put that in parentheses or it won't work. Yes, sir? No, that's different. Negative 22 would mean that this number would flip over. You're confusing that. We can talk about it later, but it's not. That would not be right. All right. So 1 over 22 and negative 22, just think about it. 1 over 22 and negative 22 are quite different. All right. This is a really, really small number, and that other one is a very negative number, and that's different. All right. So final answer, B, is equal to, what did you get? 1.02 what? 08, okay. So then, wouldn't you agree that rounds to about 2% growth? The 1.02, that's B. So now I'm going to write out my equation. Y equals the original starting value, 44,500, times B, which I know now is 1.02. Do you get how that's 1 plus 0.02? That's 2% growth. Does that make sense that Minnetonka could add 2% growth since I've been here? All right. And why hasn't Minnetonka had a ton of growth? It's a nice place to be and everything. Why don't he have much growth here? Expensive to live here. That's true. One of the biggest reasons is that all the housing spots are already taken. So back when I got here, it's not like there was a lot of vacant houses, right? They already had people in them. So some people have died, some people have moved, but new people have moved in, but still, Minnetonka has the same number of houses as it used to have, or maybe a small number of increase. Because there's not many places to build in Minnetonka, because it's already taken. Now, if you go to Wayzata, they've had much bigger growth than us, because they have a ton of like farmland kind of area nearby them, where they can, sell off this huge plot of 50 acres and put a whole bunch of houses in there, and that makes growth. Okay, we don't have much growth because it's already a well-established area. Okay, anyway, this is an equation. It's what you wanted to get for this problem, but what if they then asked a follow-up question and said, when will the population get to 80,000? Well, then it's not that complicated. If you've gone to the work of making this equation, now you have something where they can tell you a time and you'd put it here, or they can tell you a population and you'd put it there. So again, if I wanted to say population is going to be 80,000, I'd put in 80,000 right here and I would solve it. Now, how do you solve something like that? This gets weird because it's got a power of x. Technically, you need logs, but don't worry about that. We have a calculator, and calculators can solve any problem with graphing. Telling you, that thing at the beginning I told you about, graph both sides, see where it crosses, that'll solve so many problems. On the ACT, it typically solves like 10 of the ACT questions. If you graph both sides of an equation, see where it crosses. It solves all like everything. This is another one. Graph this, graph that. Remember, these are y equals, like y1 is this and y2 is this. It doesn't really matter. Graph this, graph that, see where they cross. And that'll tell you what year. And what if it says like year 33? Well, we got to then go back and figure out, okay, well, really we were in the year 1992 was like 0, so you can like do your 33 added on to the 1992. Anyway, you might have to do some adjusting at the end, but basically graph both sides and see where they cross to get an answer like this. Now, I know it's a really big number, so you'd have to jack your calculator out like way, way, way out to be able to see it, you know, do a zoom out, zoom out, zoom out, or change your window to be like reading to the 90,000 in the Y direction. But that's the big like overview of how to do this. So let's go back and see how, I'm going to go back in time here with my undo thing and see what we started with. We started with two times and like populations. And then really quickly we did that. You remember the blue stuff there? Don't forget that. You got to set it to 0 for your starting time. And then we made an equation where we stuck in the starting value. And then we made an equation where we stuck in 22 there and 70,000 there. And then we solved it for B. And when we got B solved, we knew that B came out to, we had to do that weird power thing. B came out to 1.02. And then I rewrote the equation, and there it was. That was the big moment. From there, if they'd have told you a time, you'd stick it in for X. If they tell you a population, you stick it in for Y, and you solve. Solved by graphing. All right. That's mainly the new thing that you needed to learn for today. And I will do another one with you, but otherwise it's pretty much review. One more thing. When you graph the two equations, and they come out like this. And let's say that this one is y equals 7 times 1.03. That's it's 0.33 to the x. And this blue one is like y equals 7 times 1.20 to the x. This was again a 3.3. Then, if I said when is, let's call this f of x, and let's call this g of x, when is f of x bigger than g of x? And I'd have to say, oh, when is the green one bigger than the blue one? In this zone is where the green one is bigger than the blue one. And so we'd say from 0 to infinity. That's the other major kind of problem you've had. All right, I try to do a lot of reviews so that when you hit the test, it isn't as scary to try to remember all this old stuff. Not for a while. I'll give you the exact date if I look it up after we're done with the video here. Okay, so I want to do one problem with you once you get your worksheet. So here comes your worksheet. I'll pause while I hand these out. All right, so remember that that's called a basic logistic function. And that top number is the limit to growth. So on number 7 in your packet, what is the limit to the growth? What is the highest it can ever be? Good, and that's the answer to 7C. New York's maximum sustainable population. What was the population in 1850? Well, wait a minute. Did they just give you a time or a population? They gave you a time. Now, if you were to change it over, since 1800 is kind of like your starting value, 1850 is 50 years later. How much time has elapsed? All right. So where would you put that? The T? Yeah. And E, don't ever put anything in E except what? What is E? About 2.718, yes. Okay. Let's move on to look at, I really can't have you skip any of those because they're all so important. Oh, and there's one kind I forgot to talk about, and that's called half-life. We better do one of those. Look at 8A. We'll do that together. All right. Actually, that's not the kind I was thinking of, but I'll do 8A with you. But first, I want you to stop, put your pencil down for just a second. Let me talk you through the basics of half-life. This is really quick, and in there'll be a nice, easy point someday. So here's a half-life question. If I have something that is shrinking by a half, do you get that that means if I had 10 grams of it to start with, I'd put a 10 in front? Does that make sense so far? And if it's half-life, I'm going to lose half of it. 1 minus 0.5. Does that make sense? Isn't 1 minus a half the exact same thing as a half? So I could have put a 1/2 right in here, but I kind of like to keep with this theme of growth versus decay and use the 1 minus 0.5 thing. Okay, so there's half-life. And let's say that it happens, though. In the real world, they usually give these in like days. The half-life of uranium is 64 days or whatever. Okay, well then, if it's 64 days, then I go x over 64. Because you have to factor in how many days, right? If you don't just say half-life is this, you have to tell how long it takes for it to dissolve to half of its value. Okay? I shouldn't say dissolve, that's not the right word. Decay, I think, is a better word. So let me give you one just like this. See if you, I'll leave that there for now. See if you can write this one. Polonium has a half-life of 23 days. Polonium has a half-life of 23 days. Write me the equation for that. There's one thing you need to ask me still. How many grams are you starting with? Let's say 2 grams. You got 2 grams of polonium. And it takes a certain number of days to get down to half the life, or half of the amount left. And how many days did I say? 23. So then you'd say y equals 2 times half, which could either be this, or it could be 1 minus a half. Either way is fine. And then that is to the x, and what have I forgotten? Over 23. There's a half-life problem. Okay, now go back to number 8 in the packet. Number 8 gives you a formula for half-life, which looks different, and it's okay. It's using E, because E is one of those numbers that's actually really kind of important in the real world. So they give the formula like this, and it's actually a lot like what I just said. 20, that means I must have started with 20 grams. E to the negative 0.000, how many zeros and then 3 zeros and then a 1216 T. There we go. If they gave me a time, I'd put it here. If they gave me a starting value, well, actually I already did. Starting value is right there. And if they gave me a how much there was left, well, not a time, but how much of the substance is left, I would put it right there. Okay, so look at number 8A. What was the initial amount of carbon-14 present? Oh, for Pete's sakes. Initial amount means starting amount. So what was it? 20. That was easy. Part B. How much is left after 10,400 years? That sounds like a time. Where should I put that? T. You stick that in for T. Yes, you'd need a calculator to do that. Did you know that there's an E button on your calculator? Instead of typing 2.718 to the power of, you can say E to the power of. And E is on your calculator. Let me see if I can find it on one of mine. Give me directions to it. Caret. There's a little E somewhere. Help me find it. Sorry, my calculator, somebody rubbed the buttons down so much I can't read them. Oh, there it is. It's above the divide sign. Second divide. That's the E. It's right above the divide key on your calculator. If you want to be sure that that's the right one, just say like E times 2, and you'll see if you're getting the right one. E times 2 should be about, well, think about it. If E is 2.718, it should be like a little less than 6. 5.43, yay, that's it. Okay, so it's the one above the divide sign. That's the E. That'll come in handy when you're doing this problem. As you say, 20 times E, and again, I'd use the one above the divide key, to the power of negative 0.00011216, etc. If you have to solve for t, though, remember, graph both sides and see where they cross. If you're going to put in a number for c, like I suppose we do that, there we go, a c, part c on the thing, is to put in a 10 right here. Then I would graph both sides and see where they cross. It's a little bit of a pain, but once you zoom out and you find where the second calculated intersect, that's how you do that one. All right, I can have you skip a few here. We can skip 9. Probably should do 11. We should skip 12. We can skip 16 and 15. Let's skip both of those. That ought to do it. 15 and 16 was the last two I had you skip. All right, it's all I have for the video for today.